Okay, so our talk is named The Revenge of the Script Kiddies. Most of you probably know the term, but Script Kiddies refers to young people running scripts that they didn't write themselves during their free time to hack different things, usually not in a very experienced way. But in the next 50 minutes, what we're going to show you is that scripts is no longer the property of just Script Kiddies anymore, but rather a tool in the hands of much more sophisticated and advanced attackers. Okay, let's dive into the agenda, and then we'll introduce ourselves, and then to our content. So we'll start by presenting banking Trojan, or financial malware, or bankers. We call them all these three names. It's interchangeable for us, so just so you know. After we do this short introduction, we'll present 3 different examples of scripting languages in different phases of banking Trojan's attacks. So we'll see infection, we'll see the download, we'll see code execution, and we'll see encryption and decryption. Finally, we'll conclude and go on to the rest of the amazing talks that we have here. Before I forget, I don't think many of the organizers are here, but we'd like to thank them dearly for having us here. This is an amazing event, in my own opinion, and it's a pleasure to be here. Okay, so my name is Ophir. I'm a security researcher in a data center and cloud security company named Guardicore. I'm part of the labs team, and we have a nice website that you can check for our publications. I also wrote a tutorial on reverse engineering about a year ago. If you're a beginner to the field of reverse engineering, you're more than welcome to check this website and tell me what you think, and or we'll take it from here.
Thank you, Phil. So hi, everyone. My name is O. I work for Proofpoint, part of cloud security team. First of all, we would like to thank Tostir. This research was mostly conducted in IBM labs while we worked there, and we want to thank them for allowing us to present it here. So let's start. What's the basic concept of financial malwares? So they have to wait for an online session to take place before they can start hijacking the session. That fact makes them want to infect as many machines as possible, as fast as possible. It's very crucial, and we'll show an example later on of how Ramnit did it. Also, it's important to note that the target is the end user himself and not the bank. The malwares aim to steal money from the end users. Sometimes the bank will give them the money back, but still they want to take the money from the end user themselves. So yeah, the end goal is money, and they achieve it using 2 ways. One is in session, where the fraudsters will transfer money from the victim's account to their account or the mule account that they made before. And the other way is just swapping accounts. So when you try to transfer money, the money will actually go to the victim, to the fraudster account instead of your account, or the PE account. For example, when you try to transfer money for a friend, the malware will change the number of the bank account, so it will go to a mule account. Another way is account takeover. Malwares use remote access tools. Also today, most banks use browser fingerprinting, which means that they want to know what plugins the user have on the system, what's the encoding for the languages, what's screen resolution, and they fingerprint all of it. When fraudsters try to do ATO, they must mimic all of those properties. So what's the flow of financial malware? First of all, usually it all starts with spam campaigns. After a spam campaign is sent, users usually bite the bait, and the machine gets infected. After that, malware will try to get persistency and to gain control over the browser. After having gained control over the browser, he will usually try to perform some web injections, or basically will try to alter the web page itself and change the context that the user sees. We'll show examples later on. And the other thing the malwares try to do is to redirect the user to a completely fake website. Also, we'll see an example later on. And eventually, they want to get profit and have a great success. So spam campaigns, we all know and love them. There's no real need to get into those. Most of the malwares begin with spam campaigns. Then they achieve persistence using startup folder, registry keys, task scheduler. We all know and love the gig. Today we'll show you some cool tricks that Ramnit and Gauzy does. They still use the task scheduler, but they have cool tricks. Then they aim to control over the browser. It's usually done by code injection and hooking of API functions. Most of the time it's done by using Windows function create remote thread. So on the right side, you can see Firefox function PRRead and PRWrite being hooked and jump to some unknown place of malware code. What's now nice about hooking these functions is that malware don't need to handle SSL encryption and decryption. They get the data already in clear text, so they just take it before or after Firefox has already done the encryption or decryption for them, which is cool. And on the left side, we can see TrickBot, Core DLL, and Core Parser injected to browser. And this one is not working. Nice. You have another one? OK. Yeah. Stopped working. Yeah, so as I said before, there are two types of attack, web injections and redirect. In web injects, the malware basically insert malicious code into the original web page source. They actually alter the page, the HTML code, whatever they want to do. And in redirect attacks, they will usually redirect the user to a fake website, completely tailor-made to fool them. So the website will look exactly like the original banking website. It's just a completely fake one. And let's see example for those two. So first of all, I have to say that we are not allowed to show real bank examples, so we did the best we could. So on the left side, we can see Google and username EM Bugachev. He's trying to log into his email account. And Google is saying that they will never ask him for his grandmother's favorite preferences. And on the right side, after the malware altered the page, we can see that now they actually ask for his grandmother's favorite pet. And they will say that Google will never ask for your favorite pizza. So usually it works for most users. They can't tell the difference. The other way that malware uses is just redirection. So again, we can't show real banking web page. So just imagine My Little Pony betting as real bank website. What you can see is that the address is still there. The icon, the SSL icon is still there. The website icon is there. The topic is there. Everything looks exactly as it should be. But instead of getting to your bank website, you get into completely tailor-made fake website that's made entirely to steal your credentials or details or just fool you. So now that we know that malware does it, we have the question of how it knows which targets to attack. And the answer is malware configurations. So the malware store the attack in configuration files. Usually they will be encrypted. On the left side, we can see TrickBot stores his configuration, config.conf file. And on the right side, we can see Gauzy stores his modules and configuration inside the registry. It's also encrypted, so there is not much we can read here. After the encryption, it will look something like that. So now we have a TrickBot list of servers, IPs, and ports that it tries to connect to in order to fetch modules from. Below that, there should be a list of targets that TrickBot trying to attack. So there should be a target and what to do when you reach the target. On the right side, you can see an example of real injection. So you can see the function getLogin. It verifies that the username and password exist and the user entered them. And then it calls a function calls copy string to clipboard, which basically steals the username and password via the function above. Now Ophir will continue.
Thank you, Or, for the nice introduction. Do we have a clicker? I can't live without the clicker. Thank you. OK, so as we promised before, We had a nice overview on banking Trojans, and now is the time to actually get into some real examples. So the first banker we're going to talk about is named Ursnif or Gozi or ISFB. Again, different names. We call the same family the same thing. Okay, so just a little bit of background on Ursnif. This is a malware sample that's been around with us for many years. Actually, the source code of Ursnif leaked in 2015, and this led to many of its modules being used by other malware families as well. So the most recent one I can think of is Danabot, for those of you who know. Danabot used Ursnif's web injection modules. So the actual JavaScript code that is injected to the browser during the session was used by other malware as well. Now, these are exactly the modules I was interested in when I worked in IBM, because we investigated the JavaScript code that was injected to the browser, and we signed this code to detect malicious activity in the banking sessions. So to investigate those modules and this code, we had to actually infect our own machines, and this was not an easy task at all. The first attempt we tried was trying to infect completely clean machines and fetching a sample from the wild and just double-clicking the executable file on a clean machine and hoping for the best. But this didn't work because Ursnif's command and control servers went up and down almost on a daily basis. So we just didn't manage to download configuration onto the machine. And we didn't get any web injections, of course. So the other approach we tried was to run a sample on a machine which already had the malware configuration. And what we basically did is we fooled Ursnif to think that it was running on an already infected machine, when it actually wasn't. We just had the configuration in the registry, and we thought that running the sample would this time work. But once again, this didn't work. We wrote a very nice Python script that took registry values. Actually, I forgot to say why we had access to the registry at all. We had access to end user's machine because we were getting, from time to time, reports on fraud. And we were able to connect to machines in the wild which were infected. So under full agreement of the end user, we were able to read the relevant registry values and fetch the malware samples as well. So what we tried to do was to read the registry on a victim's machine and copy the relevant values onto our virtual machines and then run the DLL on this machine. But this didn't work as well. So our second approach didn't really work, and there were no JavaScript injections to the websites which we knew were targeted by Ursnif for sure. So we had no choice, and we had to take a deeper look into the malware. And what we found out was that Ursnif cared for a value named security identifier, which is a per-user value that Ursnif used as a randomization seed to generate names inside its configuration. So what we were actually missing was to take our virtual machine and give it the security identifier of the remote machine that was infected. So what we had to do was basically add another step to our Python script and use this tool named SID change, which is available online. We just changed the SID of our local machine. We fed the local registry with the values we saw on the victim machine. We ran the DLL, and this was actually successful. And we could see the JavaScript code doing web injections and redirects and everything that Ursnif was doing at the time. But things are not so fortunate all the time, and Ursnif decided to go fileless completely. And so we didn't have any executable to run anymore, and I looked sort of like that. We decided to read the registry because this is the only thing that we had. So we've taken a look into the registry values. And as you can see, much of the data was just hexadecimal values, huge ones actually, representing both the configuration of Ursnif and its actual modules. But among all these, where's the laser here? Do I have a laser? I don't know if I do. There's one line here with capital S as a key. Never mind, where you can actually see plain text code. And this is PowerShell code within the registry. So a lot of hexadecimal rubbish, but one entry, which is actual code. This was interesting. A nice thing to mention was that when we double-click this entry, this is what showed up. Nothing. Windows registry doesn't display data which is too long. So we knew that this data could be exported, of course, and we took all this code and dumped it into a file. And this is what we got. Now, I shortened the strings a little bit just to make things more readable, but this was the actual script, the whole script. It was 5 statements long. We had 2 function declarations, as you can see, 1 variable assignment in between the functions, and 2 invoke expression statements. How many of you read or written PowerShell code? OK, that's nice, not too many. I'll just say that IEX, invoke expression, stands for the evaluation function in PowerShell, which means it's taking a string and it treats it as if it is code and it just executes it. So the equivalent in Python, for example, is eval, I think, or in JavaScript as well. OK, so let's dig into this code. Actually, we can see right away that the 2 functions are handling base64 data. We searched the documentation a little bit, and we saw that the first one was converting base64 data into an integer array, where the second one was using the first function to convert base64 to an actual string. So this part we knew. The next thing was to figure out what the data was, what this variable was. So once again, we decoded base64 data, dumped it into a binary file, opened it with our favorite hex editor, and this is what we saw. There was a lot of opcodes, of course, but then we ran into this part where many function names appeared. So we see the C runtime functions like memcopy. We see Windows API functions like create process. And at this time, we realized this was actually like shellcode payload. OK, nice. That's some information for us. We can assume that it's somehow executing code here, but we still have some more insights to draw from the script. So let's go for the first invoke expression statement. When we decode what's within the parameter, this is what we get. A lot of PowerShell code. Let's clean it up a little bit. Actually, this is too long for 1 slide, so I split it into 2. What we can see that Ursnif is doing here is it's creating a PowerShell class whose members are Windows API functions from kernel 32 modules. So we can see get current thread ID, open thread, key user APC, and sleep. And in the second part, it's creating yet another PowerShell class where it imports get current process and virtual alloc. So at this point, we can kind of assume what it's going to do. There's some thread management here, some memory allocation. Something is fishy, and there's, of course, the payload, the shellcode itself. But to really make this whole picture complete, we'll take a look at the last statement that we have here. And the last invoke expression evaluates to this. So as you can see, we have the exact functions that Ursnif was importing from before. Let's prettify this thing to have the punch of this script. So Ursnif is actually allocating memory in the current process that's running, which is the PowerShell context. And it's allocating just enough memory space to populate the shellcode. As you can see, payload length. And it's giving it read, write, and execute permissions. And then it copies the payload onto the newly allocated buffer. And then it just runs this code by providing queue user APC with the buffer address and the current thread. So this is how Ursnif is executing code using the registry value. Now, as you can see, it does it by creating the classes and importing Windows API functions. Now, how does all this get run in the first place? So Or mentioned before that banking Trojans are still using very classical methods. And as you can see, what Ursnif is using here is the task scheduler, which is a very classical trick. But actually, there's a twist here. It's not running an executable file because, as I mentioned, it went fileless, so there is no executable file to run. Instead, what it's doing, it's running a completely benign program built in Windows named for files. And if we zoom in to the value that is being triggered with every scheduled task, this is it. So it goes through the Windows System32 folder, and it's just iterating on all the files there recursively. And it's looking for a file that matches this blue pattern over there. I don't know if you see. p*LL.*e, which matches PowerShell, of course. So Ursnif is looking for a file for the PowerShell executable, and it provides it with the EC flag, which stands for encoded command, and there it gives it base64 encoded command to execute. Let's employ our best trick and decode this data, and this is what we get. So PowerShell once again invokes an expression where it fetches the registry value with the actual PowerShell code. So this is end-to-end how Ursnif is executing malicious payload on the victim machine with every reboot of the machine because it's persistent without having a file on the file system. Why is it using script at all? So first of all, fileless malware is a stealthier malware in the sense that it evades antivirus scanner engines more easily. So if you know, the scanner engine just periodically scans the file system looking for signatures, and Ursnif is obviously escaping these checks. Also, all the malicious activity is done from within the PowerShell program, which is allegedly benign and is part of Windows. So yeah, this is Ursnif and its usage of automated scripts. And the next example will be the Ramnit malware, which Or will present.
Thank you, Ophir. So before I want to talk about Ramnit, I want to talk about 3 topics in Windows, so we'll all be in the same level. The first one is Windows DPAPI, or Data Protection API. So basically, it's simple cryptographic API that's been around since Windows 2000. Microsoft provided it for developers to have easier life, to encode, encrypt, and decrypt data. It enables symmetric encryption of any kind of data, which is nice. It has 2 different scopes. One is current user and one is local machine. When you use the current user one, if you decrypt something, only that user will be able to open it. And if you use the local machine, the data will be available to all users in those machines. The good thing about local machine is that when you encrypt using it, you can actually get some files from the machine and decrypt it locally. And current user, the encryption is based on the hash of the password of the user. And this all sounds very promising. If you click on the link, you'll see a lecture that was given last year saying how not safe it is. So basically, you can tell us everything, but your secrets are not as safe as you wish they will be. Benjamin Delpy tweeted some time ago that friends don't let friends save passwords with DPAPI. And he said that it's almost like clear text passwords. However, today many applications use it for legitimate reasons. Chrome, for example, use it to save all of the user's personal data, the passwords, everything inside the browser. Mimikatz can pretty much fetch everything from your DPI information. And it has also a decryptor that was written by Nearsoft a long time ago that you can just give them some files and it will decrypt it for you. Another term I wanted to talk about is LOLBAS, or Living Off the Land Binaries and Scripts, and also libraries. It was coined by Christopher Campbell and Matt Graber. They built a cool repo. Currently, it has 96 binaries, which is basically a list of files that you can use post-exploitation. You just enter a Windows machine, and those files should already be there waiting for you. It's a list of files and whatever you can do with them, or how you can abuse them to do things that usually you're not allowed, or not supposed to do. I'm mentioning this because Ramnit uses LOLBAS, and we'll see it shortly. And the last term is AMSI, or Anti-Malware Scan Interface. It's part of Windows 10. It's an interface standard that allows application to integrate with anti-malware products. It's not limited to Windows Defender. Every anti-malware can integrate with it, and most of them actually does integrate with them. It was already bypassed a few times. On that link, you can see CyberArk passed it. They used memory patching to do it. And the reason I'm talking about AMSI is because Ramnit is abusing it also. We'll see it shortly. And now we can talk about Ramnit. So Ramnit is operating since 2000. It got taken down in 2015. that fact doesn't hurt him or doesn't interrupt him from disturbing new versions almost weekly. The latest known financial model is named Camellia. They name each model, which is cool. In campaign not so long ago, they were able to infect 100,000 machines in 2 months, which is really, really cool. As I said before, malware has to have an active session, so they want to infect as many machines as possible. 100,000 machines in 2 months is very fast and exactly what the malware wanted, so they succeed in that. Ramnit comes or can load any model they desire. They have the HVNC model, which is hidden VNC. This allows them to trick browser fingerprinting tools, so they can just connect to your machine, have a remote connection, hidden remote connection to your machine, open your browser, and connect to the banking website. It also comes loaded with keylogger, screen logger, cookie grabber, form grabber, managed browser injections, and more. And what's nice about Ramnit and most advanced financial malware is that they can create and add new modules in a very fast time. So how did I get to Ramnit? While I worked for Trusteer, someone called and said, I have a sample. I need you to have a look at it, and he sent me some files. And I just double-click it, and nothing happened. And we did the same experiment a few times. And after a few times, I just opened the scripts. And I saw that they used some function called unprotect. After some researching, I realized that this function was part of DPAPI. We will see it shortly. So eventually, I just infected a machine with Ramnit and saw that there was this randomly generated name, HBX something, that runs every 15 minutes after login. And what this task is doing is basically calling WMAC, which you can see it and read about it in LOLBAS. And WMAC is calling a VB script, which resides in a ROI something folder. And now let's go into the folder, into the scripts. So you can see that the folder has 3 files, a TXT, a VB script, and a PowerShell script. And when trying to opening the VB script, it looked a bit obfuscated. Just let's prettify it. Now it's much more readable. Now it's easy to see that they look to check whether your system is 32 bits or 64 bits, and they open the appropriate PowerShell version. Then they try to run PowerShell in a hidden window while bypassing the execution policy of Windows. It seems to be a hard task to accomplish. Then they call some PowerShell script. We will now look at the PowerShell script. So I opened the PowerShell script, and this is what I saw. A little bit unreadable, just renamed some variables. Now it's much more readable. So we can see that they took some TXT file, read it, and then call a function called unprotect. This function is part of Windows DPAPI, and the scope was local machine. So basically, the malware encrypted himself using Windows DPAPI, and now it opens that. That means that if you took the files to your own machine, you won't be able to decrypt it yourself. You have to do it on the victim's machine. And in order to decrypt it in the victim's machine, it's really easy task to accomplish. All you need to do is add this line, out file, and now we will have a pretty output with a complete TXT file. We'll see it really soon. So this was the original text. I don't know about you guys. Most TXT files on my machine looks better than or more readable than this one. It's obviously encrypted. So now we have the decrypted file because we did it before. We used the out file function. And this is what it looks like. It's pretty readable. You can read it. It has some meaningful names, but obviously, as you can see, the topic, it has some random names. So I started browsing the file, and I saw that it has 2,600 lines, which is a lot. And all of a sudden, I bumped into a remark over there. Now, that comment said, this is still get-pork address, but instead of PowerShell converting a string to a pointer, you must do it yourself. And I was thinking, wait, this doesn't really look like yourself. Obviously, he copied it from somewhere. I just put this comment on Google, and Google yielded invoke reflective PE injection, which is part of PowerSploit. Basically, it allows for reflective PE injection via PowerShell. It's a really cool tool. My next step was to compare the original version to Ramnit's version, so the version on GitHub. On the right side, we can see the version of GitHub. On the left side, we can see Ramnit's version. So you can see it's pretty much the exact same thing. He just obfuscated it really badly. So we changed some function names. He used the bad obfuscator when it really made our life easier. Now we wanted to see what Ramnit actually added to the code. So we just browsed to the end of the file, and we can see this thing. Initially, we saw this function with reflection assembly load, some base64 string. So all we did was decode the string, put it inside a binary file, and load it with our favorite .NET decompiler. And now this is what we got. You can see that the function name is disable, and it includes a library called amsi.dll. After that, he does get proc address to some function in AMSI, change the protection, creates new buffer. Basically, it's hooking 101. Obviously, the malware is hooking AMSI functions. We talked about it before, about what is AMSI. And it does it in order to avoid detection. He actually used the same method that CyberArk published. He just changed the buffer a bit. So that tells us that Ramnit is up to date and reads blogs, which is cool. So now we know that the function does disable AMSI. We can rename it to disable AMSI. We also noticed that the malware has some output strings, some debug string left, which is also bad OPSEC. And we see that it calls disable AMSI. Then it declared our original file name. Basically, Ramnit don't want the dropper or the malware itself to stay on the machine. They only want their payload to be on the machine. So they declare our file name of the malware that we ran. They stop it, delete it. And eventually, you can see that they create a new payload that starts with 4D5A. As most of you probably know, it's the magic header for MZ. So we can guess it's an executable file. And then it does invoke reflective PE injection, which basically loads that file into PowerShell and runs it from PowerShell context. And that's most of the script's job. And now let's just recap. So the architecture was a scheduled task that ran the lolbes wmac.exe. That called the VB script. The VB script ran the PowerShell. The PowerShell read, decrypted, and ran the txt file. And yeah, the question is why script? So Ramnit did it for multiple purposes. He decrypted the txt file using scripts. He bypassed AMSI. He did some code injection using scripts. Actually, it's a bit hard for antiviruses to detect it because of the encrypted payload in each machine. Ramnit did a pretty good job because he used many scripting languages, VBScript, PowerShell, the task scheduler trick. He also have a complex architecture, as we just saw before. It took some time to unveil everything and to figure out why it does every step of the way. And that's it. Phil will now continue with some BackSwap.
Thank you. So BackSwap will be our last example, and more particularly what drops BackSwap onto the machine, which is a dropper named OSTAP or nemucod. Some background on BackSwap, as we do for all malware. So this malware was first spotted in March of last year. It started by actually targeting Polish entities like banking institutions and cryptocurrency exchange platforms, but soon it realized that apparently there's more money in Spain, and it moved to attacking and targeting the 6th biggest banks in Spain. Now, BackSwap is using simple yet very, very cool techniques to do its gigs, to do its web injections and the information stealing, and I'll show you some examples. First of all, BackSwap is using bitmap images to hide its binary code within benign programs like Ollie Debug and WinRAR, for example. So it actually uses images, and it's been using Putin images as well as Cartman's bottom. Also, a nice thing I saw when I investigated BackSwap is that the actual code injection to the browser was done through the address bar. So I just open a banking website, and all of a sudden I saw the URL disappear from the address bar and some JavaScript code pasted there. So it was a matter of a second, but I could actually see that. And that's a very ridiculous method of injecting code to a browser because it's very visible. Also, the injected code actually stays in the browser history. So if you type JavaScript in the address bar, you can actually see the code that it injected. BackSwap was very, very nicely researched, and there are absolutely great two blog posts that I've read and I highly recommend. One is by Michael and Peter from ESET, and the other one is The Evolution of BackSwap, written by Ty Cohen from Checkpoint. If you want to further read on this malware, then I really recommend. So let's do some story time. When we worked in Trusteer, a customer contacted us and told us that there was a fraud case in a victim's machine. And the nice thing was that the end user was just willing to share the sample with us. And we were obviously very happy because samples are great, right? And so we agreed. And in turn, we got these. So there was some archive file that when we extracted, this is what showed up. 8 JSE files, some sharing the same size, as you can see, but all have different hash values, so 8 distinct JSE files. We had no idea what these were, actually. This was definitely not a sample. We're very used to binary files and exes and stuff like that, so yeah, what was that? We just decided to perform the shortest and dirtiest analysis we could. And this is going to be the next example of BackSwap. So we opened the files, or one of the files, with our favorite editor, and this is what we saw, a lot of rubbish. This was not fun to see, but our next step, of course, was to ask Google what JSE was, because to be honest, I never ran into JSE files before. And we saw that these were JavaScript encoded files. And of course, obviously, the next thing we had to do was to find a decoder for these files to be able to read them. And we found this project on GitHub named SCRDEC. We simply ran it on each one of the files, and we got some readable, nice files, a little obfuscated, but this is obviously nicer than what we had before. OK, so we had now 8 files. Each one had around 60K lines of code, resulting in 500,000 lines of code that we were definitely not about to read. But we decided to just take a brief look to see what's in there, and we noticed that each one of the script files started with 2 function declarations. Each one is calling the unescape method on some parameter. And each one of these functions were called thousands of times from within each script. So we figured out these were important functions, and we decided to just print out what they had to offer. Now, since they were called thousands of times, we figured out that they were decoding something, and we decided to just add our own variable to each one of the scripts. Here, we named it accumulated string. We added one more line to each one of the functions to actually append the unescaped characters to our new variable. Then we ran this thing on an isolated machine, of course, because once again, we didn't know what these scripts were. So we ran it from the command line, and this is what we saw. Nice, plain text, decoded. And the even nicer thing was to find out that this was connecting some machine, some remote machine. At this point, of course, we understood that what we had in our hands was a dropper, or droppers in plural, and definitely not BackSwap sample. But we were smarter at this point, and we could actually fetch, or try to fetch, the sampler from the command and control servers. Of course, we Googled all the indicators that we saw, like some parts of this URL. And we saw that this was the OSTAP, or Nemucod dropper, which worked closely with the BackSwap malware. And this was also covered very nicely by CERT Poland. Yeah. So this is the end of our quick and dirty solution. BackSwap, by the way, a nice anecdote, it's also moved from JSE to PowerShell, which indicates some trending PowerShell usage in the world of malware, which is interesting. And after all these examples and real-life case studies, we can now conclude what we've seen today. So banking Trojans, financial malware is moving more and more functionality from binary files to scripting languages. And we saw the scripts integrated in various parts of the attacks. So we saw the infection itself with the download of BackSwap. We saw code execution from the registry, for example, with Ursnif. And we saw how Ramnit was using scripts to encrypt data specific per the machine it was running on. Why are they using scripts? So we mentioned that a little as well. Scripts are easier to hide from antiviruses engines. And also, I would like to say that malware authors are just as lazy as malware researchers, and scripting is easier than compiling C code. I don't know, maybe some of you think differently. I like writing in Python. And eventually, this thing works. I mean, they get all the functionality they want using these methods. So they still manage to make a hell lot of money out of their cybercrime, and yeah, this is it. So we're done here. Thank you very much for being here at 9 o'clock in the morning.
Yeah, thank you so much also for you. It was a very great presentation.